Hello, IB. We're going to take a look at 13D today, which is all about constant velocity problems. And I'm recording outside, so if you guys happen to hear any cars pass in the background, you guys will know what that is, or any beeping, hopefully not. But looking at our constant velocity here, think about a constant rate of change. So we're traveling in a linear direction, and we have this constant rate of change, which we're using as our direction, since it's our velocity vector. So our velocity is, again, a vector that we're using. Both magnitude and direction are included in our velocity vector. So a few examples that we started this chapter 13 with, we'll kind of come back to here as we go into the first few examples. But we have a velocity vector. If we're given a velocity vector of -4, 3, remember you have to have some kind of initial position, all right? And then once you have that initial position, you can be told what direction to travel. So just like when you're graphing a line, you need that y-intercept or some kind of point to start with, and then you've got a direction to tell you where to plot your next point. So now that we're using vectors to talk about motion, we need an initial point, and then we need a direction to travel in. So if this were our path of linear motion, our initial position would be the 5, -1 as our position vector, or we can also talk about it as the point 5, -1. Then we also have our velocity, our direction vector, which is the -4, 3. And then we can talk about the speed as the magnitude of that velocity vector, which would be then the square root of -4 squared plus 3 squared. Okay, so then we wind up with the square root of 16 plus 9, which is 25, so we have 5, and whatever this one is in meters per second. Okay, so just a few items that we are already familiar with that we're starting to put together as we head into our examples today. At the beginning of chapter 13, you guys had an example of a yacht that started at point 220, and it was traveling in the direction of 4, -3. And every unit of time, which I think was every hour in this example, it was traveling another 4 units to the right, 3 units down, and it was kind of moving in this direction here. So our resultant vector, which we're using R to use to describe it, is showing how you have this initial position A, we have a velocity vector of B, and so for every unit of time, we're just going to continue to get the next point along this path. So what we'll wind up doing in the next few examples is writing out the actual equation for what our linear path will look like. So again, you guys will have some kind of position, initial position, and then you'll have for every unit of time some direction as well. Okay, so we can call that, I guess, B1, B2 for this one. All right, so let's see how that actually plays out. So for this one here, going back to the first example, what if your speed tripled in the same direction? Okay, well, if we tripled our speed, then what we're looking at is our speed was actually 5. We take the square root of 16 plus 9, we would get 5, I think it was meters per second. So if I wind up tripling our speed, let's say we wind up traveling for 3 units of time, what would wind up happening here? So if I started with x, y as our resulting position, we start at 5, -1, and let's say my speed triples, so that means I maybe are moving -12 and 9. What would happen if I wound up taking the magnitude of that velocity vector? So let's say my velocity actually comes out to be the square root of -12 squared plus 9 squared. So we wind up with the square root of 144 plus 81. So we're looking at the square root of, that's 144 plus 81. So that's 1, let's see, 2, 25, which winds up being 15. And that is 3 times our initial speed of 5 meters per second. Okay, so just looking at how this winds up translating for some of the problems that will be coming up later in the chapter. All right, guys, so just going through this example 9 from your book and looking at some of the common vocabulary. An object is initially at 5'10", so again, here's our initial starting position. We're moving in a direction of 3, -1, so 3 in the x direction, -1 in the y direction. So 3, -1, that's our velocity vector. It says find the position of the object at time t minutes. All right. Well, we don't know exactly how much time has passed, but we want a position. So a position being an x-coordinate and a y-coordinate. So if you take a look at what our actual equation might look like, it's good to always start with that equation because it gives us a good sense of where we actually are. So this particle starts at 5'10". For every unit of time, it travels in the direction of 3, -1. So we can say that the position is going to be at an x-coordinate of 5 plus 3t and a y-coordinate of 10 minus t. And that is our position of this object. The speed is going to be the velocity, the magnitude of the velocity vector. So our speed will wind up being the square root of 3 squared, so 9, plus -1 squared is 1, so the square root of 10, and that is meters per second, per minute. Part C, the position of the object at t equals 3. So when our time is equal to 3, we can go back to our position of 5 plus 3t, and we can sub in. So our position is going to be 5 plus 3 times 3, and 10 minus 3. So our position winds up being, that's 9 plus 5, so we wind up with 14 and 7. And that's our position at time of 3 minutes. And then our last piece here is the time when the object is due east. So if the object is due east of 0, 0, if you guys think of your coordinate grid, due east, here 0, 0, would be somewhere here. So that means we are really looking for our x-intercept. And when you guys are looking for your x-intercept, we let your y equal 0. So we're going to take our y position of 10 minus t and force it to equal 0 so that we can say that at time of 10 minutes, this object will be traveling due east of 0, 0. So it was coming down this direction from 5, 10, so up here somewhere, and then going 3 to the right, 1 down, so traveling in this southeasterly direction. All right, so the time when the object is due east would be after 10 minutes. All right, so just some common vocabulary coming back into these examples. Now let's take a look at 3 that are a little bit more interesting. All right, guys, number 3 from your section 13D. I'm going to set up a few of these with you. However, I'll leave most of this for you guys to try. A remote-controlled toy car is initially at the point -3, -2. It moves with a constant velocity of 2i plus 4j, and the distance units are centimeters. The time is in seconds. So write an expression for the position vector of the car. Again, I would start by trying to outline what this line of motion is going to look like. So we're talking about two-dimensional vectors here. We have a starting position of -3, -2, and then for every unit of time that's passing, we are traveling in the direction of 2, 4. So once I have that laid out, I can answer a lot of these questions. I want a position vector. So again, my position would be a point xy, but because they want a position vector, I'm going to leave it as a vector. So that means I could either say that my position is going to be x, so that would be -3 plus 2t, and my y position would be -2 plus 4t. Or you could use unit vector form, and you could say -3 plus 2t I. plus negative 2 plus 4t j. So either of those would be okay, but it must be left as a vector because the question asks for a vector. And then part B says, hence find the position vector of the car at time equals 2.5. So part B we'll leave for you guys, because when t equals 2.5, you're just going to wind up subbing in to that position vector that you've set up already for yourself. So we'll leave that one for you to finish. Part C, find when the car is due north. So again, if you think back to your coordinate plane, due north, sorry for all the background noises. You don't realize how much noise there is until you start trying to videotape. So part C, find the car when you're due north. You're looking for your y-intercept, since your x value would be 0. Due west, you'd be looking for an x-intercept. So you want your y value to be 0, and here you'd want your x value to be 0. Okay, from reference point 0, 0, of course. So we'll leave that one for you to finish as well, since we did something similar in the last example. And then part D says plot the car's position at these various times. So we have, again, our position vector from part A. So when time equals 0 and when time equals 1/2 and so on and so forth, you're going to get a position for each of those different times. Once you have a position for all of those times, so for example at 0, 0, negative 3 plus 0, my position would be negative 3. Negative 2 plus 0, negative 2, so that's my initial position. I'll get a coordinate for each one of these times, and then I can start to track the motion on a coordinate grid. So negative 3, negative 2, that's where it will start, and then the next point should show the direction that I'm actually traveling in. Okay, so you're going to wind up plotting a point for every one of those times and show what the path is going to look like on your grid. These 4 we'll leave for you guys, and we can check when you guys come to class next time. All right, guys, last but not least, let's take a look at number 8. Some of the more interesting types of questions that you guys can do with vectors is talking about when you have, not only just talking about a linear motion, but when you have 2 objects traveling in a linear motion, when do they cross paths or do they intersect? Trying to figure out if cars will wind up hitting each other. And in this case, with number 8, 2 submarines wind up firing a torpedo. Will they actually collide? Will the torpedo actually hit out the other submarine's torpedo? Or will it hit the boat? Or what's going to happen here? So just to get our heads around the situation, we have a submarine P that's at negative 5,4, and it fires a torpedo in the direction of 3, negative 1. So already, in my mind, I'm drawing this picture. I have an idea that submarine P is at negative 5,4, so it's sitting up here somewhere. Here's submarine P. It fires a torpedo in the direction of 3, negative 1, so it's traveling 3 units right, 1 unit down, so traveling in this direction. And I'll go ahead and put my 3, negative 1, that's my velocity vector, and I'm sitting at the point negative 5,4, and this is all happening at 1:34 p.m. So I'm just going to wind up putting this off to the side so I have everything that I need in my visual here. Then submarine Q is at 15:07. So 15:07, sitting up here somewhere. Here's submarine Q. And 8 minutes later, it fires a torpedo with velocity vector of -4, -3. So it's traveling this direction. Okay, so again, Q is sitting at 15:07, and it fires a torpedo with velocity vector -4, -3. And this is A minutes later. Okay, so for however long P's torpedo is traveling, Q's torpedo will have A minutes less of travel time. Show that the position of P's torpedo can be written as an x position and a y position, where the x position is -5 plus 3t and the y position is 4 minus t. Now again, anytime that I start linear motion, I am going to want to outline what we know. So my x and my y, and we're talking about submarine P. We start at -5,4. That's where the torpedo started. And then for every unit of time, it travels in the direction of 3, -1. As soon as I wind up writing out that equation, I notice that the x position is going to start at -5, and it's going to move with 3 times every unit of time. So you can already see where that's coming from. And then 4 is the starting position for the y, and it moves at -1 times every unit of time. So again, you can see where this is going. We know how to find speed now, so I'll leave that one for you. Show that the position of Q's torpedo can be written as this here. So again, I'm going to start the same way. I'll outline what my linear motion should look like in terms of the equation. And then this whole t minus a, remember that for however long P's torpedo is traveling, Q's torpedo will be traveling a minutes less because it left a minutes later than P's torpedo was fired. So again, this t minus a is probably going to have something to do with how that time is calculated. And then will they actually wind up knocking each other out? So in other words, will they cross paths? Well, how have we always tested whether 2 lines will cross each other's paths? We wind up setting the components equal to each other because we want to know if they will intersect. So again, all of these ideas are familiar. We're just now doing them in terms of using our vectors and a linear motion to describe what's going on with these 2 torpedoes. All right? Go ahead and try this number 8. We'll start with it next time. Otherwise, have a fantastic night.